So in the first of these videos, we looked at the London forces, otherwise known as instantaneous induced dipole forces, and we said those dipoles were temporary. In this video, we're going to be looking at permanent dipole forces. That's forces that are in addition to the London forces, but are permanently there due to the difference in the electronegativities. So in the previous pack, we looked at polar molecules, and we said that a polar molecule is said to have a permanent dipole moment and a distorted electron cloud. So in this case, it is the last three of these which are polar. CCl4 is a non-polar molecule because it's a symmetrical electron cloud and the bond polarities cancel out. If we use the next one, CHCl3 as an example, this is an example of a polar molecule. The reason it is a polar molecule is that it has a distorted electron cloud. In other words, I've got a delta positive end and a delta negative end. There is then a force of attraction between one molecule and the next. And I've got a delta positive there. Doesn't really matter where I draw that on my molecule. So that should be dotted, Cl and a hash and a Cl there. So there's this permanent force of attraction between the delta negative end of one molecule and the delta positive end of another molecule. And unlike London forces, where those dipoles are constantly changing, in this case they don't. So in this case you've got a chlorine which is always going to be delta negative and a hydrogen which is always going to be delta positive. The most important thing you need to remember about them is that they work in addition to the London forces. So the London forces are still there. This is a force of attraction on top of those London forces. So we can now use both London forces and permanent dipole to explain the difference in boiling points. So the two we're going to compare are ethene and fluoromethane. The first thing we need to think about is the number of electrons. So ethene has 16 electrons and fluoromethane, H3F, has 18 electrons. So because they're quite close in terms of their electron number, therefore the London forces are similar. If anything, fluoromethane has slightly more electrons, but that's not going to help us explain the difference between the two because the difference is relatively large. However, CH3F, this is a polar molecule, therefore it has permanent dipole in addition to the London forces. So because it's a polar molecule, it has the permanent dipole forces, and these work in addition to the London forces. Next, we're going to compare butane and propanone. Butane has 34 electrons, but is a non-polar molecule. Propanone has 32 electrons. Propanone, on the other hand, has a C double bond O group, which makes it polar. This polar group means that you can undergo permanent dipole forces of attraction in addition to the London forces. So again, we have the similar number of electrons, and therefore the London forces are going to be similar. If anything, propanone would have a slightly weaker London force because it has slightly less electrons. However, because the molecule is polar, you get the permanent dipole attraction, and therefore it requires more energy. One thing you do need to be careful of is that you're comparing like with like. So it's important that you only compare permanent dipole if the London forces are similar. So for example, if we think about molecules like HCl, HBr and HI, the HCl molecule is very polar. There's a strong dipole between the hydrogen and the chlorine due to the large electronegativity difference. By the time you get down to hydrogen iodide, that electronegativity difference has dropped and hydrogen iodide is barely polar. However, as you go down the group, the boiling point increases, even though the dipole decreases. And the reason for this is the same as going down the halogens themselves. The number of electrons is increasing. So as you go down the group, the number of electrons increases as you go from chlorine or chloride to bromide to iodide. Therefore, the London forces are stronger. Therefore, more energy is required to separate them. So it's the same argument. So the increase in electron number is more than enough to offset the reduction in the permanent dipole. This also helps us to explain why, of the 4 molecules at the top of the page, CCl4 has the highest melting and boiling point. The reason for that, even though it's a non-polar molecule, that extra chlorine with its extra electrons is more than enough to offset the fact that it is a non-polar molecule. The last type of intermolecular force we're interested in is hydrogen bonding. And hydrogen bonding, you can consider it to be a special case of permanent dipole. It is the strongest of the intermolecular forces and accounts for the relatively high boiling point of things like water, ammonia, and hydrogen fluoride. The thing we have to remember is that fluorine is the most electronegative species. Everything is based on a comparative scale with fluorine. Fluorine has an electronegativity of 4.0. Oxygen and nitrogen are also very small and highly electronegative. And it is these 3 which can do hydrogen bonding. Chlorine, although it has a high electronegativity, it's too large. As with bromine and carbon, is not electronegative enough. So only nitrogen, oxygen and fluorine can undergo hydrogen bonding. The 3 halides that we're going to be interested in are the ammonia, NH3, water, H2O, and hydrogen fluoride, HF. They have very high boiling points compared to the other hydrides in their group. So we have these 3 molecules. They are all polar molecules because they have a large electronegativity difference between the hydrogen and either the nitrogen or the oxygen or the fluorine. The nitrogen, oxygen and fluorine also all have lone pairs. Now, the molecules are polar. They already have London forces. But everything has London forces. The reason that these 3 have such an abnormally high boiling point is down to this hydrogen bonding. So we're going to take water as our example. There's a large electronegativity difference between the oxygen and the hydrogen, and this is going to make this hydrogen very delta positive. This delta positive hydrogen can then be attracted to the lone pair of an adjacent oxygen on a different molecule. And this is what we call a hydrogen bond. Notice that this bond angle here between the oxygen-hydrogen and the hydrogen bond is 180, and it's important that you can be able to draw those with the dipoles on lone pairs and showing the correct bond angle.